We're going to talk about rates, and starting off, we're going to give this generic equation of A plus B gives us C plus D. When we are first talking about rates of reaction, we are always only focusing on the reactant side of the reaction. Okay, so we can say that the rate of this reaction is going to be equal to a value of K. Now this K is something we will determine at a later time. This is a rate constant. To the concentration of A at a specific time to an X power times the rate of B to a Y power. So what this is right here, this is a simple rate expression. And what we're going to be doing here shortly is we're going to be determining what the X's and Y's are going to be. This is also called a differential rate law. Now we will talk later possibly about what an integrated rate law is. An integrated rate law will specifically have some type of factor of time within it. These do not. These are at a specific point, but not over a distance of time. So the example we're going to go over will be the following reaction. If we take ammonium ion and reacting it with nitrite ion to produce nitrogen gas and 2 water molecules in a liquid form. Now remember too, when we do kinetics, we're only dealing with the reactant side here, or at least determining here for what the rate law is going to be. So what we'll do is we will do an experiment, and what you should have for a problem like this is at least 3 different experiments, if not more. These experiments have concentration of both reactants and the overall initial rate of the reaction itself. All right, before we move on here, we're going to set up 3 different experiments. We'll have the initial concentration of ammonium, initial concentration of nitrite, and initial rate. Now, before we move on with this, we need to make sure, I'm not going to show this, but concentration is in moles per liter or molarity, and the initial rate is in a unit of moles per liter per some unit of time. This unit is seconds for what we have right now. So here is our experimental data for 3 experiments. We see that we have molarity for the ammonium, nitrite, and also the initial rate of the reaction itself. So what we're going to do is we're going to take 2 experiments and we're going to divide them by using the initial primary or the basic rate law. So I'm going to take experiment 1, and I'm going to divide that by experiment 2. Now, the reason why I picked these 2 is that one of them will divide out. We see that if we take the experiment 1 for the ammonium and experiment 2 for ammonium, we'll see those will divide out and give us a factor of 1. You'll see what we're talking about here in a minute. So I can say that rate of 1.35 times 10 to the negative 7th is equal to K. The initial concentration of ammonium is 0.100, this is to the X value, and 0.0050 to the Y. And we're going to divide this by experiment number 2, which is 2.70 times 10 to the negative 7 is equal to K, 0.100 to the X, 0.005 to 0.010 to the Y. So we can see what happens here is that we have K's that will divide out each other, and the 0.1 divided by 0.1 gives us what's left over. So what we can do is we can divide So after we cancel out, this is what we have left. So what we do is we divide both sides. 1.35 times 10 to the negative 7th divided by 2.70 to the negative 7 comes out to be 0.5, roughly 1/2. And then we take 0.005 to the y divided by 0.01 to the y. We come out with 0.5 to the y. Now, just by knowing some simple powers, we know that y must equal 1 because 0.5 to the first power is 0.5. Now, with some other problems, these might get complicated later on, so I want to show you something called the rule of logs in terms of solving for these. This expression right here can be viewed as this. If I can take this, I can say the log of 0.5 is equal to y times the log of 0.5. And now I can algebraically solve for this now. Y is equal to log of 0.5 divided by the log of 0.5. And that also gives us y is equal to 1. Okay, so there is our first exponent we solve for y. So we can go back to the original expression and we can change this. Let's do that now. So we can take the initial rate expression here and we can say that this is now to the first power or first order. Now what we're going to do is we're going to solve for now what x is going to be, and then we'll have our rate expression. So now let's solve for the variable y, or x, sorry. We're going to be looking now at experiment 2 and 3, and we can say that our rate of initial rate is 2.7 times 10 to the negative 7 is equal to k. 0.100 to the x and 0.010 to the first. Now we know it's the first because we saw for that in the last one. Remember that these numbers are coming from the initial concentrations of experiment 2 and experiment number 3. Now let's look at experiment 3. We see that we're going to have 5.40 times 10 to the negative 7th is equal to k. And we see here that our concentration of ammonium is 0.200 to the x and 0.010 to the first, and that's the concentration of the nitrite. Now we see here that k's cancel and also these cancel, giving us the result of 2.70 to the negative 7th divided by 5.40 to the negative 7th, which also comes out to be roughly 0.5. And 0.1 divided by 0.2 comes out also to be 0.5. Okay, so without going through the rule of logs, we know that this has to also be first order. So we can go back to our initial rate expression, and we can say that this right here is also to the first order. We can say now overall, this is second order reaction, because what we do to determine overall order is we take the orders or the exponents we have determined from the rate problems, and we can say overall it is second order. I hope this has been not too confusing, and if you have any questions, please leave it down in the comments down below. More chemistry content will be posted at a later time on YouTube, and please subscribe if you want to have more videos and some more examples being done.